Welcome, alert physics students, to Chapter 8 already. Boom. Chapter 8. We're going to talk, the big deal in Chapter 8 is what we call the conservation of energy. Huge deal. Vast deal. And the name of the chapter is kind of long-winded. It's potential energy and the conservation of energy. Okay, so we're going to do potential energy first, but before we do potential energy, we have to cover section 8.1, which is about what we call conservative and non-conservative forces. Okay, so here's the thing. There's two kinds of forces in the world. Well, actually, there's more than that, but you can divide them up in a number of ways. One way you can divide all the forces in the universe up is conservative forces and non-conservative forces. Nothing to do with politics, okay? Nothing to do with being liberal or whatever. Has to do with something totally different, okay? Same root, of course, conserve, do not change kind of thing. But there you have it. Two kinds of forces, conservative and non-conservative. First thing I want you to imagine here as we discuss this is that we're going to have a box. It's going to, or just a mass. It's 1.0 kilogram mass. And we're going to raise that mass up 1 meter. Okay. So the distance here is 1 meter. Okay. And then we're going to bring it back down. We're going to go up. We're going to come down. Okay. And so the question is, round trip this is what we call a, let me see, where's the phrase here? A closed path. Because the object ends up where it began. It would still be a closed path if we took the mass and, took it around, Saturn and brought it back. And as long as it ends up back where it started, it's called a closed path. And we'll come back to that term very soon. But what I want to know is, for this round trip up and down, what was the total amount of work done by gravity? Okay. For the round trip, what was the total amount of work done by gravity? Well, it's a simple question with a simple answer. Let's do it. Now, let's see. Let's say on the work on the way up. Work on the way up. Well, work is force times distance. Force times the displacement times the cosine of the angle between them, right? You remember this. Work done by a force is equal to the force times the magnitude of the displacement times the cosine of the angle between those two vectors, right? Become one with this. Let it merge with the rest of your thoughts so that when you need to know it, you'll have it. So let's see. What force we're talking about? The force of gravity. The question is, what is the round trip work done by gravity? That is the question. Now, what's the direction of gravity, right? Well, gravity is down, right? Gravity is down. Weight is down. So on the way up, right, we have the force, which is going to be mg, times the distance, which we're going to call d here, right? D is the meter here. That's the magnitude of the displacement. Times the cosine of the angle between the displacement, which is up, right? Because this is the up part, up, and the force is down. So a cosine of 180. And the cosine of 180 is -1. So it's going to be the mass, which is 1.0 kilogram, times 9.81 meters per second squared, times 1.0 meters. times minus 1. Do your math. You can see very simply here with two significant figures. This comes out to negative 9.8 joules. That's the amount of work done by gravity as the block moves up. The mass, whatever it happens to be. Okay. It's negative because the force of gravity is down, but the displacement is up. That's 180 degrees. Whenever a force is opposed to the displacement, the work done by that force is negative, always. When a force is opposed to the displacement, the work done by that force is negative. All right, so work down. Now, displacement is down. Gravity is still down, so the two are now in the same direction. It's going to be, again, mgd times cosine of what angle now? What's the angle between the force of gravity down and the displacement? That's 0. Cosine of 0. Cosine of 0 is 1. So that's 1. And what we're going to get when we put our numbers in, same three numbers, we're going to get 9.8 joules. So gravity does negative 9.8 joules worth of work on the way up. It does positive 9.8 joules of work on the way down. So the total work, how do I have it written here? The work done by gravity by the round trip is negative 9.8 plus 9.8 joules, which is 0. Actually, I'm not going to draw my zeros like that because I haven't been doing it all along. I'm not going to start now. So the work done by gravity for the round trip is 0. Okay? It is 0. That's for the force of gravity. Okay, so round trip, gravity does no work. Let's take a different situation now. Same mass, similar kind of situation, same 1 kilogram mass. My pen is really running out of gas here. We're going to have the same displacement. We're going to push it 1 meter, but now we're going to push it across a tabletop with friction. We're going to say that the coefficient of kinetic friction is 0.30. Pretty normal. Okay, that's, you know, if you put your book on top of your table in the kitchen and slide it, that's about 0.3. So this is pretty normal. So we're going to push it now to the right 1 meter, and then we're going to return it to the left so that we have yet again a closed path. We have two closed paths in both cases. Remember, that means that we start and stop at the same location. Okay? In both cases, both that one and this one. And now what I want to know is what is the round, the word round starts with R. The round trip work done by friction. In this case it was 0. Gravity was 0, right? That was our answer. Round trip work done by gravity, here was 0. Now we want the round trip work done by friction. Okay? We're going to do the same kind of mathematics. Work to the right. It's going to equal the force of friction kinetic friction. So that's the force of kinetic friction is mu sub k mg. Right, that's the force of kinetic friction. That's F sub k. Cosine of what? Cosine of what angle? We're going to push, right, this is to the right. We're taking our mass and pushing it across the table to the right. As we push it to the right, the displacement is to the right. What direction is the force of kinetic friction? It is to the left. That's a small drawing, I know. I should have made it a little bit bigger, but sort of squeezing myself out of space here. So the displacement is to the right. Force of kinetic friction is to the left, so that angle is going to be 180. The cosine of 180 was -1 before, and it's still true. -1. So we put in our numbers here. I'm not going to write all the numbers on the board, but if you take 0.3, which is mu sub k, times the mass, which is 1.0, times gravity, which is 9.81, you end up getting the work done by friction is -5.8 joules. That is for the rightward push. Okay. Now we're going to turn it around and bring it back. Okay. Before we were pushing it to the right, and the force of kinetic friction was to the left, because the force of kinetic friction always opposes the motion. Therefore, when we now push it back to the left, here we go, what's the direction of the force of kinetic friction? It is now to the right, because the force of kinetic friction always opposes the motion, unlike gravity that's always pointing straight down. Whether the block is going up or coming down, gravity is always down in both cases, coming and going. Okay, over here, the direction of the frictional force changes direction when the block changes direction. So when we do work done by the frictional force as the block goes to the left, we're going to get the same mu sub k mg. Oh, I forgot to put, made a mistake here. I don't know if you noticed it. I did need to put d in there, right? Because it's force times distance times the magnitude, to be more precise, the magnitude of the displacement. So that belongs there. Just like d showed up there and there, it's the force times the displacement. So that d, let me circle it in pink. That was where I left out. That right there belongs in there. So as we push to the left, back to the story, now cosine of 180, oops, I should be using yellow, cosine of, we have cosine of 180 yet again, do we not? Because the displacement is now to the left and the force of friction is pointing to the right, so they are 180 degrees apart, right? Like that little dance there. So this is still equal to -1. And so we get the same thing. Okay, so what we get here, oh, it was orange that I was using. This is right. So what we're going to get here is again the same thing, -5.8 joules. Okay. I wasn't trying to emphasize this. I was just using the wrong color marker. D. So you get the same thing. Whether you're pushing the block to the right, pushing the block to the left, work done by friction is the same. Which means that when you add it all up, the work done by work done on the round trip here is not zero. It's not zero now. Now it's going to be -5.8 times 2, which is negative, let's just say -11, because that's to round it up. to round to two significant figures, what we get is that the work done by friction for the round trip. How about that squeak, huh? This is again for friction. I should say kinetic friction. Okay. So in one case, a force does zero work on a closed path. On the other case, a force does non-zero work on a closed path. This might just be, in some senses, this sort of interesting little fact about friction and gravity, but it points to a much deeper, very significant point, which is that gravity is known as a conservative force, and we'll see why soon enough. Conservative. Friction is known as a non-conservative force. Okay. And the thing about the conservative force is that it does, conservative forces always do zero work. How's the phrase? On a closed path? On a closed path. Along a closed path. Any force that does not do this is a non-conservative force. Conservative forces do zero work along any closed path. So it doesn't really matter where the block goes. If I take this block and I take it around Saturn and back and bring it back to where it started, the work done by gravity on it will be zero. But as long as it ends up where it started, okay, the work done is zero. That's because we call gravity a conservative force. Friction, not that way. No matter how we scoot this thing around, friction is always going to do negative work, so it'll never add up to zero. Gravity can do positive or negative work, so it can cancel out. Friction can only do negative work, so it can never cancel out. The more we slide the block around the table, the more and more negative this number gets. Conservative forces, non-conservative forces. We will see very soon why this distinction is important. Okay? We'll see why this distinction is important. See you then.